Chapter 8, Perceiving Motion. So we perceive motion in a number of different situations, obviously. The two fundamental situations that we perceive motion are, the first, where we are stationary and we are observing objects passing in our field of vision. We're seeing things moving in our field of vision. Or when we're moving and we see things moving in our field of vision as well. As you might expect, both of these motion perception tasks are distinct in many ways. They require different sorts of processes to make them happen. So we're going to be talking about the different types of processes that are in play when we're observing, either when we're stationary and we're seeing things in motion, or when we are moving and we are observing other things moving. Why do we perceive movement? Well, obviously it's an important skill. It's survival. One of the key things that predators use to detect prey is movement perception. So predators like, for example, a cat or a fox will listen very closely or watch very closely for evidence, for stimuli that are telling them that there's some piece of meat, a prey object moving that they can get to, right? So they use the motion of prey to locate their prey. So as a result of this, right, one of the things that is really important for a predator in this environment is attentional capture. That is the paying attention the moment you see something move. You may have seen this, for example, if you have a cat and you've been playing with them, and you notice how cats, will orient real intently to to like a toy that's moving, or if you move your hand underneath the sheets, they'll orient towards it. That's a very natural behavior for cats, because cats are obligatory carnivores. That's all they can do is eat meat, and everything they eat has to be caught by them. So they're the perfect land predator, basically, and use that to use the motion to capture their prey. So on the other side of the coin, we have the prey, right? So if you're a prey like a mouse or a rat, and you want to avoid being caught, what would you do? Well, you would remain motionless. If you remain motionless, then your predator is going to have a much more difficult time locating you. So this is why a lot of animals, such as rats, for example, will freeze when they become scared. So if you scare a rat, if you frighten a rat enough, like with a prey scent or with an electric shock or something, it will not run. What it's going to do is it's going to freeze. And that is a survival skill that evolved as a result of the fact that the predators were using motion to detect their food. So the critters that were able to remain motionless were more likely to survive and thus pass on their genes to the next generation. There is a very strange brain disorder, the result of brain damage, akinestopsia. That's blindness to motion, where you cannot perceive the movement of objects. It's a very strange disorder. When we watch things move, we tend to ascribe to the objects moving intentions and motivations. So this picture here is from an old study that was done back during World War II. And what Hyder and Simmel did in this study was they had people watch this very simple film, just this flat black and white film of these simple shapes kind of moving around. So the shapes would kind of move around, come next to each other, They would go out to the door, go out through this opening together, then come back in. And what they found was that as people watched these little shapes do their little thing, they would ascribe motivations and make up stories about what they were doing. So when we are watching things move, part of what we're doing unconsciously is ascribing intent and meaning to the things that we watch move, motivations and things like that, even personalities. Obviously, perceiving objects and events movement is a critically important survival skill. And as I said earlier, we're either looking to understand how we are moving through objects or how objects are moving relative to us. These two fundamental types of movement, these two fundamental types, tasks, processes, however you want to call them, underlie a lot of how we organize our world, right? So we do organize our world around the way things move around us and the way things move towards us and away from us and next to us and whatnot. Now, this is an interesting illusion here. I wish I could. I was actually trying to make this happen, but basically, what you do is you would take this bird here, and this is a bird, right? It's a bunch of lines, but we perceive it as a bird, right? So, and if you superimpose that bird over a part of this jumble of lines here, you can put it to where these lines correspond exactly with some of the lines that are here. And you won't be able to see the bird because the lines will be overlapping with the lines that are here. But then if you move the bird, all of a sudden you can perceive the motion. All right. So the bird is camouflaged by being hidden in the background. We don't perceive it until it moves. And then as soon as it moves, our brains work to organize these jumble of moving lines into something that we can understand. And in which case, that something we can understand is going to be the shape of a bird. When we observe things move, one of the things that we see is the different shapes and textures of an object as it moves, right? So if you watch this car coming at you, turning left and then heading off in that direction, we perceive it as a car, even though if you look, for example, at this picture versus this picture, these are two completely different images, right? This is the front of a car and this is the side of a car. They look completely different. But if we watch this motion, if we watch this object moving across and doing its thing, doing its turn, our brains have no problem detecting this motion, and not only that, but also knowing that this is the same object, even though it looks quite the same going from here to here to here. We have this continuity that tells us that this is the same object, and also we get all of the different perspectives on the object so that we understand its three-dimensional structure. I'm sure some of you have seen some of these illusions. This is a little foal, a little baby horse laying on the ground. And it looks like a whole three-dimensional horse, but when you get behind it, it's really kind of flat and weird looking. That's because as we're getting around it, we see its true shape, right? It reveals its true shape. Again, this motion, this ability to move and maintain an understanding of a particular object is what gives us our ability to see all three-dimensional aspects of a particular object. Two types of motion that, I should say three types of motion that we study in motion perception are, first of all, real motion, and this is basically where an object really is moving. So if you're watching a car go across the street or watching a ball fly through the air, that's real motion. Illusory motion is where something looks like it's moving, but it really isn't. Illusory motion is usually made up by putting together very quickly a bunch of stationary things that aren't moving and then making it look like they are moving. So for example, the video screens on your phones, laptops, and TVs if you're watching a video on your computer or on your phone, there's nothing actually moving on your screen. What's happening is that your screen is getting refreshed many times a second. And that refresh is changing the pixels each time, but it's doing it so fast that you don't see the refreshes, and it looks like there's motion appearing as those pixels rearrange themselves several times a second. There's no movement there, but it looks like it's moving, and this is how movies and television work. There's also induced motion, where the movement of one object results in the perception of movement in another object. So for example, if you are in a parked car and there's a car parked next to you, if that car rolls slightly back, it'll look like sometimes you'll feel like you're going forward. Or if that car goes slightly forward, you'll feel like you're rolling back. I drive a standard transmission vehicle. So when you drive a standard transmission vehicle, you have to be really careful about if you're in neutral and you don't have your foot on the brake. If you let go of the brake, the car will start to roll back or forward depending on what the incline is. And some people can trick you that way. You're sitting together in a car and then they'll pull up forward and it makes it look like you're going back, right? So this is an example here of illusory motion. I can flash this light first, then it goes dark, and flash this one very quickly thereafter. If I flash them at just the right rate, it'll look like this square is moving from here to here. This is the basis for, like I said, for video screens, but it's also the basis for these rolling marquees that you see. These marquees that you might see like in Times Square, New York City or something. It looks like these letters are rolling across the marquee, but in fact it's simply the lights moving very quickly in sequence to make the letters look like they're floating across the black part of the marquee. There's a really interesting phenomenon called motion after effect. You can actually see this, an example of it here on this waterfall. So if you spend about a minute or so staring at this waterfall, now of course what you're seeing is the water flowing down the cliff into the little lake below. So if you spend about a minute just staring at that water, at this water, and then quickly look away here, you're going to see like this little kind of like fluttering of waves going up in this opposite direction. And that is called the motion after effect, and it's probably due to the receptors in our retinas that have become adapted to watching this movement in this direction. When you move over, when this movement goes away, it rebounds, right? The receptors rebound, and for a brief moment for a few seconds, you see this after effect, this rebound effect here of movement going in the opposite direction. Okay. So Larson wanted to see if okay, so let me back up. So if we go back to this slide here, right? We know that there's a difference between actual motion and this apparent motion of this light going back and forth, right? So what Larson wanted to do was to see are there brain differences between when we perceive real motion and when we perceive apparent motion. That's what he wanted to look at. So he put people into an fMRI, which is our favorite tool to use, and had them look at three things. First, the control group was looking at two dots in different positions, and they're flashed simultaneously. So I'm looking at the screen, and then boop, boop, the dots flash. Real motion is where the screen showed a dot, and the dot was actually moving back and forth. So there was no flashing. The dot was simply moving back and forth like this. And then finally, apparent motion is where they had two dots flash like that, so that it looked like the dots were moving like on the marquee. Right? So we had the control condition, two dots flashing simultaneously, real motion, and the apparent motion condition where the dots were flashing like that. Right? So in the control condition, each dot activated a separate area of the visual cortex. And that makes sense because this dot would say be up here and this dot would say be up here. They're two separate objects. And they're going to be illuminating different parts of the cortex. The motion dots activated the visual cortex very similar to each other in the apparent motion and in the real motion, which tells us that even when we're perceiving apparent motion, we're using the same part of our brain, so the same part of our visual cortex that's used in perceiving real actual motion. So here's the evidence, right? So this right here is the cortex. And I'm yeah, this would be the back of the head right here. This is the occipital lobe here. So this is the back of the head. So we notice that when we flash these two dots simultaneously, it looks like you can see both dots represented in the visual cortex. When we do the apparent motion, the real motion of the dot going here to here, and it actually is a dot that's moving back and forth on the screen. We get the dots lighting up, but we also get this area of the visual cortex lighting up as well, telling us that we're detecting motion. And in a very similar fashion, the apparent motion, where the flash, where it looks like it's moving, lights up almost exactly the same areas in almost exactly the same way.